Dear students, in the last class I have discussed Bohr magneton up to here. Magnetic dipole moment of revolving electron in hydrogen atom is given by mu L equal to E by 2 m into L, where L is angular momentum. L equal to angular momentum of the electron. Angular momentum of revolving electron. But from Bohr's second postulate, Niels Bohr has given three postulates. First postulate about the stationary orbits. Second postulate is about this angular momentum, quantization of angular momentum. So angular momentum of the revolving electron in various orbits is quantized. It cannot have any value, it has discrete values. Multiple of h by 2 pi means nh by 2 pi, where n is integer. It is also called as principal quantum number. Okay, it is a natural number, n equal to 1, 2, 3, 4, etc. Now magnetic dipole moment of electron can be rewritten using angular momentum L equal to, from the Bohr's second postulate, using MEVR. This is angular momentum r cross p vectorially. L vector equal to r vector cross p vector. In first year rotational motion you studied. So that is MEVR, as theta is 90 degree. So sin 90 is 1. So MVR sin theta is MVR. Okay, MVR. ME we use for mass of electron. Okay, then it is equal to NH by 2 pi according to Bohr's second postulate. Now it's substituting this, L value is NH by 2 pi. We get the magnetic dipole moment of electron is this much. Now Bohr magneton means minimum value of this angular momentum. So in which orbit the magnetic dipole moment will be minimum? Minimum value of magnetic dipole moment of revolving electron. Mu L value minimum. So n value minimum is 1, means in the first stationary orbit, innermost orbit, n value 1. So the magnetic dipole moment will have minimum value. So that is what called as Bohr magneton. So n equal to 1, then we get Bohr magneton. Okay, n equal to 1, we get Bohr magneton. So that is the minimum value of magnetic dipole moment of revolving electron in hydrogen atom. So n value 1 if you substitute, it becomes h into E divided by 4 pi me. Okay, so this is the expression for a Bohr magneton. And then value of Bohr magneton can be asked in the exam. Value of Bohr magneton. So using the values constant, so mu L minimum equal to h value 6.626 into 10 power minus 34 into E value. E is 1.602 into 10 power minus 19. Okay, then next divided by 4 pi me. 4 into 3.14 159, okay, into me 9.11 into 10 power minus 31. Okay, simplifying, substituting and simplifying all this, we get say multiply these two numbers, okay, divided by 4 divided by 3.14159 divided by 9.1. After simplifying everything, we get 9.27 into 10 power minus 24. Okay, minus 24. Unit of Bohr magneton dipole moment, it is ampere meter square. Okay, so you may not get exact number is this much, but see the powers, minus 34 minus 19, this when you take up minus 31 take up plus 31, so then you may get a little different power. Okay, but final answer can be written as this much. So this is the value of Bohr magneton given in the book also, 9.278. So question will be what is Bohr magneton and find its value, or express its value, or write the value, or write the expression for Bohr magneton means He by 4 pi me. Mu L minimum equal to He by 4 pi me. So this is all about Bohr magneton which we discussed in the last class. Up to here I discussed. So then I go to the next topic, that is moving coil galvanometer. So galvanometer you have studied. I have told about galvanometer. Galvanometer is a device which detects, which is used to detect the presence of current. Detects the presence cannot measure how much current is there, we cannot measure. But we can make use of galvanometer into ammeter as well as voltmeter by conversion. So moving coil galvanometer, moving coil galvanometer. Galvanometer basically has a coil, okay, then there is a soft iron core, cylindrical shaped soft iron core, and then it has got a pointer, and the coil is placed inside the magnetic pole pieces. Okay, so that's the basic idea. So now here you see, this is the magnetic pole pieces. Inside the two magnetic pole pieces, that is N and S, are the pole pieces we take, and here we take the coil of rectangular cross section. So here is the cylindrical soft iron core, actually cylindrical soft iron core, cylindrical object like this, and on which we make the windings. It is not circular, remember. Cylinder means when you cut it, it is circular, but it has got height. You see the gas cylinder, so it has got height, it is circular cross section. So the coil is rounded on the cylindrical soft iron core. On this is the cylindrical soft iron core. So that is used to increase the magnetic field and make the magnetic field concentrated. Okay, so and it makes the magnetic field radial. The cylindrical soft iron core makes the magnetic field radial. Okay, like this. Okay, so this makes the field radial like this. The magnetic field becomes radial from N to S. The field direction will be N to S. And also one more reason we use for this cylindrical soft iron core, the field direction. Always the field will be parallel to the coil because of this cylindrical core. So this is the windings I will show. This is the coil actually. It is the cross section of the coil. So windings are made like this. This cylindrical soft iron core and windings are made. So the cross section of that coil will be rectangular cross section. There will be n number of turns. N number of turns of coil there wounded on the cylindrical core, and then there will be a pointer and there will be a scale. Okay, this is the scale which shows the deflection, and there will be a pointer like this. This is the pointer, and this is the circular scale which measures the deflection, and there will be markings on the scale obviously. Usually galvanometer has a central 0 mark and one side 30 divisions, another side also 30 divisions. When no current is passed through galvanometer, we have to adjust the pointer to 0. Sometimes it may not be 0, but you have to turn in the 0 adjustment screw. You have to make the pointer show 0 initially. Then whenever current is passed through the coil, passed through this coil, due to torque experienced, the coil rotates. When coil rotates and soft iron rotates, the pointer also rotates. Pointer is attached to the coil, and there will be spring. The purpose of spring is to bring back the spring is to bring back the pointer to 0 mark. Okay, so that's the brief. These are the magnetic pole pieces, N and S. Magnetic pole pieces. Then this is the soft iron core. Soft iron core. Soft iron core intensifies the magnetic field in the central region and makes the magnetic field radial, and one more advantage is that the field is always parallel to the coil at any position of orientation. The field, if the coil is turned like this, the field and the coil, plane of the coil will be always parallel. Okay, so then this is the coil here, this one is there now. So this is the coil part here, this one I have shown this way now. This is the coil part. There will be large n number of turns of coil wounded on the soft iron, and there is a spring. Okay, so this part is the spring. So this one is the circular spiral shape is shown now. So that is spring. So spring is required. So whenever the current is passed through the coil, it will show some reading. When current is off, the pointer should come back to 0 mark. Initially it is 0, so it has to reach back to 0. So that work is done by that spring. Okay. So this is about the construction of a moving coil galvanometer. Moving coil galvanometer principle is, so whenever a current is passed through a coil, it experiences a torque, because a coil is placed in the uniform magnetic field produced by these magnetic pole pieces. It is inside the field, magnetic field. Between, say, any magnet is there, surrounding that magnet there will be magnetic field. So now this coil is placed inside the magnetic pole pieces, means it is placed in the magnetic field produced by the pole pieces N and S. Okay. Now that coil experiences a torque because there is some current flowing in the coil and it is placed in the magnetic field. It experiences a torque. Due to the torque, it rotates. The effect of torque is rotation. It produces rotation. So that's why whenever coil is rotated, the pointer on the scale, it moves, because pointer is attached to the central coil and the spring, so it rotates. When current is off, the pointer is brought to 0 mark initially. Okay, so that point position it comes. So that's about the construction. Principle is, whenever a coil placed in the uniform magnetic field experiences a torque, and due to the torque the coil undergoes rotation, or it will show some deflection. Okay, so the pointer will show some deflection. And now theory of this moving coil galvanometer. Theory means how it works and how the expression we can get. Okay, so there are two terms related to this, which I can say current sensitivity and voltage sensitivity. So firstly, torque experience, magnitude of torque experienced by the coil. Okay, torque theory, right? Theory of moving coil galvanometer, theory of MCG, moving coil galvanometer. Firstly, torque experienced, magnitude of torque experienced by the coil due to the magnetic field present, uniform magnetic field I will take. So torque equal to mb sin theta, mb sin theta, but here theta is 90 degree, because I said always see the direction of area vector is like this, field is this way. Okay, so this is the direction of area vector. Okay, area vector, whenever coil is like this, area vector, and the field is like this. This is the direction of field. So what happens? Area vector and magnetic field always perpendicular. So that means theta is 90 degree. Angle theta is 90 degree. So mb sin theta. So that is for one turn of the coil. So whenever it is n turns are there, so it will be n, and m value. What is the magnetic dipole moment of a coil? It is Ia. Okay, Nia is the magnetic dipole moment of a coil, Nia. Okay, then B sin theta is 1. So this is 1, equation 1. So torque experienced by a coil when placed in the magnetic field is NIAB, where N is the number of turns in this coil. This portion is the coil actually. This is the coil I have shown here, and this is a spiral shaped spring, and this circulation, no, this is not circular, it is cylindrical soft iron core. And S are the magnetic pole pieces. This is the pointer which indicates the reading, and there is a scale. Okay. So torque experienced by that coil when current is flowing through it and placed in the magnetic field is mb sin theta. Okay, theta is 90 degree. Theta is 90 degree. Yeah? So m. Okay, m is Nia. Is the magnetic dipole moment of the coil, Nia. Okay, so Nia. Next, B, multiply magnetic field. Okay, N is the number of turns in the coil, I is the current flowing through the coil, area A is the area of cross section of the rectangular coil, B is the magnetic field here in this region, magnetic field. So now this spring is the action of spring. Spring will try to bring the coil back to its position. It will develop a torque which makes the unwinding work, means which brings back. So the torque produced by the spring, this is the torque experienced by the coil. Okay, torque produced by the spring is how much? Torque produced in reverse produced by spring is a tau. Okay, so that tau dash or tau I, right? So that is equal to, okay, torque produced by spring is equal to. So there is that torque will be directly proportional to angle. If the spring made more rotations, it will produce more deflection. So I write here k theta. Okay, so that is proportional to theta, where k is the torsional constant of the spring. K is called the torsional constant of the spring. And theta is the deflection produced in the spring. Okay, theta is the deflection produced in the spring. Okay, so now comparing. So at equilibrium, equilibrium means the torque experienced by the coil in the magnetic field is equal to the reverse torque experienced or reverse torque produced by the spring, so that it will be in equilibrium position. So the spring will try to rotate reverse, whereas because of the torque experienced, coil goes one side, it rotates one direction. Whereas the reverse torque is developed by the spring, it will bring back the spring, bring back the coil to its normal position. So at equilibrium means the two torques balance each other and the pointer shows some steady reading. Okay, pointer shows some steady reading. Assume there is no spring, or it will be continuously moving. Because of the torque, the coil should continuously rotate. It is not happening here. Means because of that torque developed by the spring will bring back the coil to normal position, or at any position it makes, whenever current is flowing in the coil, it makes equilibrium position. So now, okay, what happens, you see, the two torques are equal. Therefore, k theta equal to NIAB. So therefore, the theta deflection produced, or I can write phi also instead of theta, k phi, where phi is the deflection produced. Okay, phi equal to NIAB by k. Okay, so this implies the deflection. Okay, so here I can write phi is the deflection produced. How much deflection? How many divisions? Deflection produced on the scale. By the pointer. How much deflection it produces on the scale. Okay, how many division deflection it is. So deflection is measured in terms of divisions. Okay, so deflection theta equal to, we can say, I out NAB by k into theta, into I. So that means that is deflection phi proportional to the current. This is what the final conclusion. So at equilibrium, the torque produced by the coil is equal to torque produced by the spring. So they both together act and make the pointer stationary or steady at one position. Okay, so the two torques are equal. So then k phi equal to NIAB. So phi equal to deflection phi equal to NABI by k. So these numbers are constant. Number of turns, area of one loop of the coil, B magnetic field in this region, and k torsional constant of the spring are constant for a given arrangement. Hence, deflection phi is directly proportional to the current. Thus, what can conclude? The deflection produced in the coil is directly proportional to the current flowing through the coil. Deflection produced in the coil, okay, that is directly proportional to how much amount of current is flowing in the coil or through the coil. Okay, so that's about the concept. Next, there's a conclusion, actually, theory part. Then it can be asked two definitions: current sensitivity and voltage sensitivity. So current sensitivity. So the quantity phi by I is called as current sensitivity. Okay, so see the expression deflection phi equal to this much into I. So bring the I LHS. So phi by I is NIAB divided by K. NIAB divided by K. Okay, where K is the torsional constant of the spring. So all these numbers are constant for a given galvanometer. For a given galvanometer, these values are constant. Galvanometer just detects the current. It cannot measure how much current. We have to convert it to ammeter or voltmeter. So current sensitivity is phi by I, deflection per unit current. Okay. So deflection produced in the galvanometer per unit current. Okay, per unit current. So that is called as current sensitivity, and unit of this deflection. So division per ampere. This is the unit of current sensitivity. How many division deflection? Phi indicates how many divisions deflection. Then I is the current. So phi by I is division per ampere. How many division deflection per 1 ampere current? If 1 ampere current is passed through coil, how many divisions deflection it shows, it produces. Okay, phi by I is the current sensitivity, NAB by K. Okay, so that's all about current sensitivity. Next, another term called voltage sensitivity. Voltage sensitivity. Voltage sensitivity is phi by V. Phi by V. Okay, so we can write phi by V equal to phi by I into 1 by R. Agree? Because Ohm's law. Apply Ohm's law to the coil. The resistance of the coil is R. Then I is the current through the coil. Then potential difference across the terminals of the coil V equal to I into R from Ohm's law. Any coil or anything, potential difference is current multiplied by the resistance. Now potential difference across the terminals of the coil is I into R according to Ohm's law, current into resistance. So then we can write phi by V as phi by I into 1 by R. Phi by V is called as voltage sensitivity. So now phi by I already we know how much it is, NAB by K. Okay, therefore the quantity voltage sensitivity phi by V is equal to phi by I NAB, okay, NAB by K into 1 by R. So this is the expression for the voltage sensitivity, NAB by K into 1 by R. And the definition of voltage sensitivity is deflection per unit voltage. Simple, deflection per unit voltage means if we apply 1 volt potential difference across the galvanometer coil, how many divisions deflection it shows? Deflection produced per 1 volt potential difference or 1 voltage, 1 volt potential difference. Okay, so deflection per unit voltage. Okay, so this is called 1 volt deflection per unit volt or deflection per 1 volt potential difference applied by the coil. So E is called as the voltage sensitivity, and all the current sensitivity as well as voltage sensitivity are very big numbers because it is highly sensitive device. Galvanometer is a highly sensitive device. It shows a small division, a few divisions deflection. Even if you pass a microampere current, microampere means 10 power minus 6, it will show some deflection. Okay, so that is about the voltage sensitivity and current sensitivity of the moving coil galvanometer. So then how to increase the current sensitivity or voltage sensitivity of a moving coil galvanometer? Okay, and also the unit of voltage sensitivity is division per volt. Okay, division per volt is the unit of voltage sensitivity. Division per ampere is the unit of current sensitivity. Division per volt is the unit of voltage sensitivity. So this galvanometer, how to increase its current sensitivity? If you have a better galvanometer means the voltage sensitivity or current sensitivity should be larger. Okay, how to increase? See, N directly proportional, voltage sensitivity directly proportional to N, directly proportional to area, directly proportional to magnetic field, inversely proportional to torsional constant. And if you take here R value, that is inversely. That means if you increase the number of turns, 100 turns are there, if you double the number of turns, 200 turns, then voltage current sensitivity will double. Okay. Then area, if you increase the area of the cross sectional area of the coil, if you make more number of turns and make bigger loop, that is by using a bigger soft iron core, if you make the bigger coil also, then it will increase the current sensitivity. If you keep in a strong magnetic field region, if you use strong magnetic pole pieces in say here, the coil is placed in a stronger magnetic field. So magnetic field increases, it will increase the current. And using a spring of low torsional constant, small torsional constant or lesser torsional constant, so then also we can increase the current sensitivity of a moving coil galvanometer. And one more is voltage sensitivity is here. Increasing the number of turns, we cannot increase voltage sensitivity. The reason is when you increase the number of turns, for example, if you make 100 turns into 200 turns, obviously current sensitivity doubles. Number of turns doubled, current sensitivity doubles. What happens to resistance? If that coil has got 100 turns, coil has got some 10 ohm, and if I make a 200 turns coil, then the resistance become 20 ohm. 10 ohm resistance become 20 ohm resistance. Resistance doubles. When resistance doubles, so what happens when resistance doubles? The R value doubles, N value doubles, R value doubles. Both will double. So N, instead of N become 2N and R becomes 2R. So 2 cancels. So it does not increase the voltage sensitivity of the galvanometer. If you increase the number of turns into 2 times, then resistance of the moving coil galvanometer also doubles. When resistance doubles, then N by R ratio remains constant. So we cannot increase the voltage sensitivity. So remember the point, this fact, by increasing the number of turns, you cannot increase the voltage sensitivity because resistance also increases. Resistance of the coil also increases, so that ratio N by R remains constant. So we have to increase voltage sensitivity, means you have to increase the area, or you have to keep in a stronger magnetic field, or you have to reduce the value of K, or you have to use a spring of small torsional constant. So that's all about this voltage sensitivity and current sensitivity. Unit definition. Current. Okay, so 1 ampere current is passed, how much deflection it produces, how many division of deflection. So deflection produced per unit current is called as current sensitivity and expression, unit. Okay, so expression phi by I is current sensitivity, NAB by K. Okay, then voltage sensitivity is defined as deflection produced per unit volt. 1 volt PD applied to the coil here, how much deflection it produces, how many divisions deflection it produces. Okay, so then unit of voltage sensitivity is division per volt divided by voltages. Divisions, deflection is measured in terms of divisions. So division per volt, phi by V equal to phi by I into 1 by R. Phi by I is NAB by K from previous. So this is the expression for voltage sensitivity and current sensitivity is this one. Okay, so they can be asked unit definition and how to increase the current sensitivity, and if number of turns doubled, voltage sensitivity does not increase but current sensitivity doubles. Okay, so that's all about this topic. In the next class I will discuss how to convert a galvanometer into ammeter and how to convert a galvanometer into voltmeter.